You guys have a good lunch? Yeah. Good. Now you guys can take a nap. Perfect. So my name is Andrew Sutton. I am a professor at the University of Akron. I'm talking about reflection. I know this is not the title of my talk, as promised. This is a bit bait and switchy. Not as bad as the next talk, which I will explain later. But I'm going to talk about static reflection, kind of how you implement it, sort of language features. This is definitely not a big ideas talk. This is not a how you use it talk, because the language features simply aren't mature enough to generate really good examples to kind of explain the domain. So I'm talking about my work that I've done for the last 2 years. But before I start, University of Akron, that's where I work. Nice place. Apparently we will be having an esports program sometime soon. Competitive esports? I don't know. If you guys can see it, there's a little gold star. That's where Akron is if you've never heard of it. It's in Northeast Ohio. It's a lovely place. Living there is inexpensive as opposed to places further east and west near water. And less likelihood of water rushing in over your home. This is, you guys might know Akron from this company. Goodyear is based there. In fact, that is actually flying over Akron. The university is in the bottom left corner of the screen. My building is just cut off, unfortunately. But nice place. Akron is also the home of LeBron James, which I have to add because we now have the LeBron James Family Foundation College of Education. I don't actually have to add that. I'm just a Cavs fan. And we just signed Dwayne Wade yesterday, so that's awesome. If anybody follows basketball, it's big news. Okay, so on to C++. So I got started in this work with Herb on meta classes, and admittedly it was not out of the goodness of my heart. I actually had a plan, which was to take Herb's ideas from meta classes and apply them to another project that I was working on, which has nothing to do with compilers, which is in fact software-defined networking, which complements my work with programming languages and compilers really well. But I figured it would be worth a shot, and I thought this was a good way to kind of not do front-end languages or multiple compilers for, say, packet decoders, packet generators, whatever, and that we could actually maybe leverage that to generate faster and more efficient and safer networking protocol implementations. Or at the best, or maybe ideally like fuzz testing capabilities for arbitrary packets based on a single C++ program. That seems like a really nice idea. Unfortunately, there are a lot of language features that you actually have to implement before you get from that point to the point where you can apply it. This is kind of the tip of the iceberg for that work. So in order to generate code, you really actually need reflection because you have to analyze the code you want to generate. So reflection, of course, ends up being the sort of tip of that iceberg. And so that's what this talk is about. So really briefly, overview, the obligatory overview slide that I typically hate giving, but whatever. So what is reflection? Important thing to know. We got to talk about dynamic and static reflection. I shouldn't just jump into explaining what static reflection is without explaining why every other attempt at reflection is less than good. And then basically the rest of the talk is going to be how you do this in C++, which is an interesting question. And if you think it's easy, then you have not thought about how to do this in C++. So, what is reflection? Well, basically it's a set of language features that let you write algorithms that consume your program as data and then do stuff with it. In the very broadest sense of the definition, that's really what reflection is, kind of. It's that introspection part, being able to use your program as data. The other side of that, kind of, is doing stuff with those other programs, right? So really, the kind of end goal of all of this is metaprogramming. Like we want to be able to write meta code that consumes a program and generates a program, hopefully within the same language, hopefully without a meta language, but reflection is really the entry point to all of that. Reflection enables metaprogramming, and it informs it. Right, so in the most broad sense that I could think to define this, reflection is basically just a set of operators. It translates between two domains. One domain is a set of source code entities that you might have. The other domain is some set of values that encodes that in a way that you can actually use it in a program as data. I am going to talk about different ways you can actually encode those information later. So the two kinds of operators we actually have, they go back and forth between these two domains. A reflection operator takes a source code entity or construct. I'm going to keep using the word construct because C++ has a very firm definition of what an entity is. Do you guys know what an entity is in C++?
A thingy.
Did you get an early copy of my slides? I think I actually used the word thingy somewhere. No, a macro is not an entity in C++. A function, variable, class, template, like those things those things are entities. Usually things that we can put a name to are entities, although we have a couple more things like objects and values. Those are also entities. Is an expression an entity? It is not. Is a statement an entity? No. So I invented the word construct, or co-opted the word construct to kind of build a sort of bigger set from entity. So then we have these other set of operators that go in the other direction, which are, I have this value that encodes some kind of a construct. I want to do something with it. And I am deviating wildly from whatever terminology might exist in the in literature today. I'm just calling these action operators. And I'm using the word operator very loosely also. It could be a function. It could actually be an operator. It could be a method of a class. But it's something that kind of invokes a behavior that's very internal to what the language is. So how many of you guys are familiar with Java and Java reflection? I don't know if I don't know how to feel about that. That's too many hands. So in Java, you can look up the definition of a class via the class floater. The fact that I know this is almost embarrassing. You can query that for a particular set of methods. Like that's the reflection part of it, right? And then you can actually call this function called invoke. You package up a bunch of arguments, you call invoke, and that does something very languagey, right? Like you can't actually see what invoke does, but it pushes a new stack frame, allocates a new set of locals, copies all that information in there. If it can, maybe throws an exception. So that's an action that you take, a language-oriented action that you actually take from a reflected value. Dynamic code generation, same thing. I haven't written C# in many, many years, but I understand that you can actually generate C# on the fly from reflected code. So you have some action associated with these values. I'm going to change that word action in a little bit. So every metaprogram, every useful metaprogram roughly has this kind of behavior, this kind of strategy. You're going to get some reflection of a particular entity. You're going to take some source code construct that you have. You're going to package up as data so you can write an algorithm against it. You analyze the reflection, you look at it, you decide some properties of that particular thing, and then based on whatever you see, you perform an action. This is basically how we teach CS1 students to write programs, although we never use the word meta, but same concept, right? So if I want to write a two-string function for enumerations, for example, I actually have like 4 steps in this. Somebody gives me an enumeration. I go get the type as data. That's reflection. I go get the list of enumerators in the enum. More reflection, right? We're just getting data about these objects. We might want to search for the list of, we're going to search that list of enumerators for the value that we want to print in one way or another. Okay, that's analysis. Very simple algorithm. Standard find would be great. Return the declared name of return the declared name of the enumerator. That's an action. So very simple formulas, very simple recipes. The only difference, the only things we have to concern ourselves with are really how do you get source code into values and how do you get information back out of those values or actions out of those values. So a lot of languages support dynamic reflection. A lot of languages support dynamic reflection, right? And there are some, I feel like I missed a slide. Oh, well, yeah. So a lot of languages support dynamic reflection. It's not a zero-cost abstraction. Like you end up paying for that in a particular way, right? So if you actually do have to have dynamic reflection, basically the ability to do all of that at runtime. So you can ask for the value of an entity at runtime. You can write a normal algorithm against it, and all of those actions end up being some kind of runtime system that performs that action, right? So if you actually want to ask for the name of an enumerator in a traditional language that supports reflection, you actually have to pre-cache all of the enumerator names, because if you don't, that data simply won't be there. So it's clearly not going to be a zero-cost abstraction. It can't be. Like you have to keep putting stuff into binaries because of this. Increases your binary overheads, you lose optimization opportunities. I mean, unless you're really going to be very aggressive about JIT compiling expressions in the code, that's a completely different discussion, although one that's particularly interesting in the context of programming languages. But if you opt into a language that does this, it is almost impossible to opt out of the reflection requirements. It's not possible in the case of Java at all. That's actually how you translate the code. You generate all that information you need because that's how it works, right? So why, if there's going to be all that much overhead, do you actually want dynamic reflection? Well, I mean, I guess there's some good reasons, like, dynamic method invocation or lookup invocation, that seems to be useful. Some interesting things like runtime code generation. C# does this, I believe. You nodded earlier, so yes. Then you have some really interesting and questionable things like self-modifying code. Like I usually trust myself to get a program right the first time I write it. I do not trust myself to write a program that writes a program that modifies itself and remains correct after modification. That scares me a little bit. But I think the real reason that all these languages have to opt into dynamic reflection is that they simply don't have the capabilities to compute things at compile time. Java, outside of like simple things like constant folding, if you write 3+4 in Java or C#, it's almost impossible that any good compiler would allow that to escape to a runtime operation. But beyond those simple compile time computations, these really simple expression calculations, you cannot do compile time things in these languages, period. And so anything that you want to do that involves reflection has to be pushed down to runtime decisions. And I always like to point this out that I really think this is a kind of a crutch for bad generic programming support in those languages, because I worked on concepts for 6 years, and so of course I have to say that. But really, if you look at those languages, the way that they dispatch things, that you have a generic algorithm, and then you write a bunch of if statements that kind of decompose that so you can select better algorithms later on. So the kind of specialization based on type must be runtime decisions, because there are not a lot of languages out there that can do if statements at compile time, which is really weird because it's not that hard. So, meanwhile in C++, not a problem, right? We got lots of great facilities for compile time computation. Specifically, we have constexpr. And that other thing, templates, right? So we have lots of facilities for this. We have ways that you can ask questions of types. We can kind of ask questions of declarations if we're clever and we kind of work a little bit harder. That certainly happens. Concepts, which showing up in C++20, another reference to concepts, of course, let us write queries for how a type is used, which is fairly novel. But as advanced as our support for this stuff is, we don't really have comprehensive support for reflection. We can't ask really interesting questions like, no, really, what are the members of a class? Is this member public? Is it private? Is it protected? What constructors does this class actually provide? Not how can we initialize a class, but what constructors do you actually provide? So the goal when we approach metaprogramming, one of the requirements as we approach metaprogramming is the ability to actually kind of ask those questions. You have to be able to do that. If you can't do it, we can't write meaningful algorithms, right? So hopefully I just kind of answered this really, but why would we add, actually I guess I didn't. Why would we want to actually add a reflection, like comprehensive support to the language for static reflection? Is it because we can actually write these interesting queries? No, not really. It's so that we can actually write better metaprograms, so we can actually generate better code. Right? And the reason that we actually want to do this, for me it all boils down to boilerplate. It all reduces to boilerplate. The goal should be to write less boilerplate code. If we can find some way to opt into the generation of a lot of different facilities based on a few parameters or a few simple invocations, that would make me very happy. The day that I don't have to write operator equal and not equal and less and greater and whatever, I can just provide like eq and less and not use the curiously recurring template pattern. That will make me very happy indeed. Anyways, so static reflection, the static version of normal reflection. Same idea, right? So we still have a set of operations mapping between constructs. In the case of C++, we are literally mapping between constructs plus expressions and statements back to some kind of value. How you encode that value again is really interesting. That's going to be the remainder of the talk. We have another set of operations or operators that go the other direction. I'm going to call these projection operators because they're not runtime. They don't actually need to do anything. What they really need to do is actually generate code. They don't act. They just turn back into syntax, right? So, reflection, abstractly. Source code entities plus expressions and values, I left that out. So, our reflection operators are going to take some kind of named entity, return some kind of encoded value. What did I say here? So this is going to support the ability to actually query like properties of a declaration. That's kind of important. We aren't looking right now, or we haven't considered deeply looking at reflecting on every possible construct. As soon as you want to talk about reflecting on expressions, for example, like this is a really cool and powerful technique. It also opens a slightly different Pandora's box, especially when you get into code generation, because now you have essentially macros, but structured. They're interesting. So we're not talking about doing everything in one shot. This is very much about declarations and properties of declarations right now. Projection operators come in a bunch of different flavors. And again, abstractly, I'm going to talk about these as kind of being one per part of grammar, because that's really the best way to talk about it. It's the easiest way for me to talk about it, right? So these projection operators, they take an encoded reflection value, something that you get from a reflection operator, and they give you back syntax. They don't perform an action, they actually give you back syntax. So for example, if you want to project a reflection value into a type specifier, you actually have to generate what that type specifier is. Or if you're writing the compiler, for example, you would just generate a type in your language. But it fits into that part of the grammar wherever a type specifier is required. If you want to project a reflected entity as a nested name specifier, you know, like when you write standard : experimental : that's a nested name specifier. So if I have a reference, or if I have a reflection of standard : experimental, I should be able to take that and project that as a prefix for whatever follows. So we're generating syntax from these things. And again, we can just do the same thing with value and name projections, right? So if I have a reflection of a function, I might actually want the value of the function. What's the value of a function? Anybody want to guess? Don't say an overload set. It's just a pointer to the function. Something that would let you call it, for example. If I have a reflection of a global variable or a member of a class, the value of those things would be a reference to the global variable or a pointer to the member of the class. So we have some way to kind of traffic between this sort of abstract data, or not abstract, but this data that we use to represent these reflections, and the grammar that we actually use to write our code. Name projection is one of my favorites because you can actually take the name of like a function and just generate a new unqualified ID for lookup later on. So there's lots of ways that we can move between these two domains. In fact, lots of ways we can move between these two domains, right? But it's not really general purpose code generation. We're not talking about taking these things and generating new declarations. Not yet, that's tomorrow morning's talk. So there's a bunch of committee work going on, and I believe this list is probably a little bit incomplete, but the work actually started with P194 and P385. 385 gives motivation, P194, there's a series of these that give you a specification for reflection. This is done by Mattis and Axel and David Sankel. I see David over there, puts his hand up. Thank you, David. There's type-based reflection that Herb and I have worked on for the last year. There's actually two flavors of that. Depending on how time goes, I will talk about the second one. And then we have a bunch of additional direction ideas from in piece 633 by David van de Voorde and Louis Dion. It should be worth noting that David actually had proposals for metaprogramming earlier in his career with a metacode system. And I think a lot of those ideas have shown up in different format in P633. And I am not ashamed at all to say that we have co-opted many of them. So, encoding reflections. Turns out there's a bunch of different ways you can do this. I'm going to talk about them each in turn. Again, maybe the most recent work last, if possible. So we can encode reflections as types. This is an incredibly powerful technique, but there's two ways you can look at doing it. You could actually take the reflection of an entity and make that just a type, or you could return an object whose type encodes the entity. And this actually ends up making a big difference. And you guys will see this immediately when I start showing you the difference between these two proposals. The alternative is you can actually just represent these as objects, which I might be able to talk about pending time. Choice of representation, the way that you do this, makes a huge difference in the way that you go about building your library compiler interface, how you use it. It is not an arbitrary decision at all. So, P194. So, reflection operator in this paper is spelled, oh, is that right, David? Oh, it's changed. Just reflexper, okay. I will change that. Ignore the $sign. There were different versions. I wasn't quite sure what was modern, what was current. So it's just reflexper. So you write reflexper int, and you can say you can using meta int equals reflexper int, and meta int is now the type. It is a type, a class that tells you what you want to know about int. This is not a particularly useful example, unless you want to know the size of int, which I believe you could just write size of int and get the same information. So the definition of the class is unspecified. These things are created as needed by the compiler. The specific properties that the class exposes are really defined by a concept. So the concept says you can ask for size, probably the name of the type. That seems to be important. I would expect, because it's a type, you can also ask if it's const or volatile or a reference. That might be a different class. So there are things that you can ask, and all of that stuff is conveyed by this concept. But the implementation details of the class are completely unspecified. And I believe that all of the properties of the class, with one exception, are encoded as static members of the class. So you actually end up generating, every time you call reflexper, something like this. It is a new class, some internally computed name for this thing, and then you just sort of spam out the properties of that class that you want to be able to access. Right? Works nicely. So if I write, and again, ignore the $, earlier draft, I apologize. So if you say using t equals type name, so, oh yeah, sorry. Projection operators are just type traits. Because you kind of pack all those traits into the class itself, you don't really have to do anything very complicated to get them back out. They're just there. So you can write a type trait or something like a type trait that simply, requests the associated member through some whatever details are necessary to compute that thing. So if I say, reflexper int and ask to get the type of the int, that is taking the reflected type class, the data for that int, and it's turning it back into a type specifier. And so now I can use that thing where I can use t wherever I need a type, which would be nice. So another example, if you have enum e with a bunch of things, you can ask for the constant of the reflection of a. So you reflect on a, that gives you a type that encodes probably the value as a static constant expression, and you can just unpack that guy with this type trait. There are some other cases that are alluded to in various drafts of this proposal, variously mentioned as unreflexper. If you're not getting a type or a value, you actually need some kind of other operator to generate a fragment of syntax. And one of the suggestions was unreflexper. Is there an update? No, okay. So I will leave that as it is. All right. So this is toString with this implementation from P0385R2, which hopefully is the most recent that's been published. I know there's an R3 that probably doesn't include this. It's a lot of template meta programming. None of this is really important except for the bottom 2 lines, but the way that it works is that you invoke this helper function to generate a static map of values to strings, and you just look it up at the end. And so this actually works nicely. Except in the case where the enumeration has 2 names with the same value, but every implementation we're going to look at today has the same problem, which it doesn't quite work. But so the choice made to encode the value of a reflection as a type, as a class, forces you to use it as a class, which forces you to use template meta programming. Now, that being said, this is a very complete solution. You can do any level of reflection and any level of projection, possibly with an extra operator too, using this system. The downside for me, of course, is that it requires template meta programming. I am not at all a fan of using templates to express computation, and this is just computation. If we can make it easier to do, we should try to do that. Right? Benefit of this approach is that there are very few compiler intrinsics. The only one that I'm kind of remotely aware of is that if you ask for the members of a class, the compiler will automatically generate you a list of types of different type, and that is I think the one interface between, besides reflexper and potentially unreflexper, I think that is the one interface between the compiler and the library. And minimizing that is kind of a nice thing to have. The downside of the approach one of the downsides of the approach is compile time performance. Every time you reflect an entity, every time you invoke reflexper, you are generating a new class. Compilers do not forget classes, ever. In Clang, at least, every time you allocate a class object, like the abstract syntax tree for a class, it stays with you for the duration of translation. It does not go away. So for long-running meta programs in large translation units, you run a very real problem of inflating the memory costs of these programs to a point where they are not sustainable. Haven't seen it yet, but it is a thing that we should be concerned with. And in fact, is a thing that the standards committee is very concerned with. Okay, so My approach, our approach, Herb's and I works. So the goal was to kind of make metaprogramming go away. Like we liked the ideas in 194 and 385. We did. It made a lot of sense. We just didn't like the angle brackets. So the goal was to kind of get that out of there and try something a little bit different. And this is actually implemented here in GitHub, ASUT, and Clang, along with a bunch of other things. I'm proud to say that the reflection capabilities in this branch are actually fairly stable, unlike the injection capabilities. But this wasn't actually all that hard to implement. Modulo a ton of bugs and difficulties. So the goal here, our reflection operator here, we spell it $, and I know the standards committee has not been fond of $, as a reflection operator, and had some good discussions with Vila earlier this week as to why. But I still like it. It's short. That's why I like it. Really, that's exactly why I like it. So if I have a function called f, I don't know, returns n+1, no big deal. I can write auto meta f, meta function of f equals $f. That reflects gives me an object that contains the reflected value of the function f. So syntactically, $$ is just a primary expression. The operand is either an ID expression, which means it refers to a function or a variable, or it's a type ID, which means it refers to a class name, or it is a namespace name, which means it refers to a namespace. So basically, the idea is you reflect on a named entity. Again, not a full construct. We don't reflect expressions just yet, or statements. That'd be weird. And it gives you back a value. What value? Actually, maybe not yet. Let's see, so yeah, what value? Well, the type of $$ is actually a specialization of a class in some namespace somewhere. We call this, it is CppX : meta : something. I left off the CppX here. The eventual goal would hopefully be standard : meta : which template you actually get out of this, or which template is actually instantiated, depends entirely on the entity you reflect. Right? So if you ask for a variable, you might get a class called variable. If you ask for a specialization of variable, if you ask for a function, you might get a specialization of function. If you ask for a class, you get class type, fundamental type. Basic concept is there. One-to-one mapping between the kind of entity that you request and the kind of template that gets instantiated. Reflected namespace is NS because you can't write namespaces in a class name in C++, sadly. So all of these templates they are parameterized by one thing, which is an encoded reference to some internal data structure. So it's the encoded reflection that we get back from these, or that we encapsulate. Oh, and by the way, I should point out that the intent was to make these implementation defined. I don't care what they're called, it doesn't actually matter. You would always just write auto, because you don't know what the type of these things is going to be. Again, you would just model some kind of concept that tells you what you can get out of it. So, you write same thing above, and you actually get the type. The template you instantiate would look like this: template reflection tx. Reflection t is not a magic type. It is in fact a type alias for standard int pointer 64, or standard int pointer t. That's it. It's just an int. It is in fact not particularly a complicated data structure at all. It is just a laundered version of the pointer to the AST node in this implementation, because that was really easy to do. So basically, every time you ask for the reflection of something, you end up instantiating a class whose template argument is a laundered pointer value. Beautiful. It could also be, by the way, an index into a data structure the compiler keeps track of. It's not in this implementation. And this is, by the way, a small area of concern for me, because reflection t is just an int. You could ask for like a projection on the value 4, and the compiler will say, sure, cast 4 is a pointer and dereference, and that's bad. So clearly some work needs to be done in this area. Not a big deal, not yet. The details of the class, we actually encode all the properties of the class as, so first of all, the class is actually empty. It's just an empty class with a bunch of static context for members. Well, for now it's empty. Tomorrow won't be. It won't be empty. So all these things are just static context per functions. Name returns a constant character pointer. Type returns whatever the type of this thing is inline, is context. They just return bool. Not particularly complicated. The definition of these things requires some library compiler interface. And that is done through intrinsics. So these are projection operators. Sorry, forgot my order of slides. So we have a set of projection operators. Some of them are compiler intrinsics, some of them are actually operators. The The implementation of those functions in particular are just intrinsics. They all start with underscore reflect. They take as an argument the reflection, the encoded reflection value, and the magic happens in these functions. Like the entire implementation of reflection happens in these functions. So what happens if you get the reflection, so if you write $int and call .name, what happens is that you don't instantiate the definition of this function until you actually call the function name. At the point that you call name, the compiler is obligated to instantiate the function definition, which means it substitutes the compile time value of x, which is at this point an integer, into this reflect name expression. And the compiler just says, hey, you're giving me reflect name and a value. I know how to get that. So it actually just goes to the AST node that was passed in, de-launders the AST node, and then just goes and asks for its name. So if you're asking for int, it'll compute int. And it replaces the reflect expression here, the intrinsic, with the string literal expression. So when you call this function, it bakes into the class, the definition, what that result is going to be. That's how all this stuff works. Keep that in mind for later. That might be a problem. So if you ask for the type of something, we do the same thing. We just have reflect type, you instantiate that, the compiler looks up the reflection, which is again just converted for cast from the AST node, or an integer into an AST node, gets the type, and constructs another object whose type would encode the type of that object. So if you were asking for the name of the function in this case, you get the type of it, and you would get a function type with parameter types and return type. Just another reflection. It works nicely. Right. Value reflection or value projection is just a property of these intrinsics also. We don't have to work too hard for this. So a bunch of variables and a bunch of functions. So we actually ended up, the first pass of this, we said that for the most part we just want to get pointers to these things back, so that's why everything is written in terms of pointers, except enumerations, of course, because you can't get the address of a numerator. It doesn't happen. So if you want a pointer to a global variable, you can ask for x.pointer, and that just calls this reflect pointer trait. Same thing. We just end up replacing these things with expressions that compute the address of that particular object. And it gives you full access to that as you go. Probably worth noting for variables at least that this will not work at all if you try to give it a local variable, because local variables do not have a constant address. That would be bad. But you can get the address of a member function or member variable and a member function. And so you can actually use that to index into, if you have an object, you can use that particular pointer to access the members of the class at runtime, which is kind of nice. Dot value for enumerators gives you the compile time value, which is kind of nice. Let's see here. Asking for the members of a class is fun because it was not easy to implement. So this gives you a tuple. Remember, every member of a class could potentially be a different kind of thing. You can have constructors, you can have a destructor, you can have conversion operators, you can have normal member functions, you can have member variables, static member variables, which are actually in Clang are not member variables, but variables. You can have access specifiers. Do you guys know you can reflect an access specifier? Turns out to be important. You can get injected class names. That's fun. So there's a lot of things that you can get in that tuple if you ask for the members of a class, or that you can get from there. And so we generate this tuple, I can't say a tuple, it's a tuple-like object that gives you access to all those members in turn. So you can actually ask for like tuple size of that thing, and it'll tell you how many members you have, although it is not a useful operation because normally people don't count things like access specifiers and injected names. If you use get0, you can get access to the 0th member, which will almost certainly be the injected class name of the type. It works nicely. I mean, it works okay. Get and size are lazy. They're just built on a couple of intrinsics. I think reflect member size and reflect nth member or something like that. I don't remember the precise names of them. I wrote it about a year ago. So we don't actually build the tuple in one shot. Otherwise, if we tried to do that, we would actually have to build an entire abstract syntax tree the second you reflect anything. And that seemed a bit crazy. So you don't want to pre-compute those values. You definitely do not want to create types of tuples for a single operation, even though it's going to stick around and be reused. Most of the time, however, these tuples are actually filtered because nobody wants all the members in a class. You might want the member variables, or you might want the member functions, or the constructors. So we actually have a little wrapper tuple that kind of tries to filter these things out. I must report that I am not the best person at working with these data structures. I'm sure that Louis, if he was here, Louis, no, or Eric, if he was here, might be able to craft a better implementation of that data structure. First pass, I got it to work, I'm happy. I will not look at that code again, it is disgusting. Anyways, which is what I just said. So the problem with this is that we actually end up with, that we still have to be able to use these different, like we have the problem now of programming with heterogeneous containers. So you go from template meta programming with type lists to programming with heterogeneous containers, and there's still a lot of overhead to this. And we still have good tools for it, like Boost HANA is fantastic. We could have foregone any kind of additional language support and just said, we must standardize Boost HANA, and that is how you will work with these template meta programs. I didn't really like that. Standards committee might have issues with it, I don't know. Vila, standardize Boost HANA?
Ask Louis.
Not here. Disappointing, I know. So the question was, can we do better? We can do a little bit better. So we ended up actually creating a new language feature on the side. Like this, by the way, this has kind of been the story of how reflection and metaprogramming go. Like you try to solve one problem, you run into another, and you create new language features as you go. So we invented a new kind of for loop. So if you write for ... and Herb alluded to this in his talk, you don't get a loop. You actually take that thing that's on the right-hand side, auto x and member variables, that's a tuple. And so you conceptually, you iterate over the members of the tuple. That's not right at all. What happens is you basically just unroll the loop so every instance of the loop body binds for the next member of the tuple. And this simplifies programming a little bit. It doesn't solve all problems. It solves a particular set of problems. It certainly makes it easier to write loops, to apply, basically to apply a particular function to every member of a tuple. Okay. So this actually ended up getting extended over the summer by a student of mine, Sam Goodrick, honor student at U Akron. We actually expanded that to include, well, tuples was done, we included to incorporate arrays, and then we said, well, why not just destructurable classes? So basically anything that you can use with a structured binding, you can also throw through this thing, so simple structs, fantastic, that works. And I think we were going to go after parameter packs too, if you have an unexpanded parameter pack and you instantiate this loop with that as the argument, you'll just unroll over the entire loop. So I expect to write a paper for this for C++20 in Albuquerque, mostly just updating an old paper. But this is actually not a bad feature. I like this feature a little bit. Normally, pack expansions expand to a sequence of arguments, so you can only expand in a limited set of contexts, usually where expressions are required. This basically takes that and linearizes it to expand over sequences of statements, which is kind of a new thing that we can do. Haven't gotten to expand over a sequence of declarations yet. That might be tomorrow. Right? So the other projection operators that we have for these things, they are currently, at least in the implementation so far, are spelled thusly. Type, name, namespace, and ID expr. Herb and I have been discussing whether or not it's possible to compress all these things to a single projection operator whose meaning depended on the thing that you project. It might be nice to simplify all these. I think in some cases it might not be possible, but again, we're still exploring the idea. And these ideas do actually come from P633. I think they were almost directly taken from David van de Voorde's metacode ideas. And the ID expr, I think, is a reference to something that appeared in an early draft of 385. So reflecting a type name is pretty straightforward. If you have a reflection value, if you have one of these objects of reflect meta : type, you just call type name, and that gives you a type specifier. So if you have meta x, you can ask for its type, pass that to type name, you get its type. But of course, if you give it a typed declaration, the operator should be smart enough to know that you actually want the type of the typed declaration, in this case, an int, so you get int. Or you could just directly go ahead and pass in the reflection of a type and generate that as a type specifier of its own. All three would give you int y whatever equals x. Namespace projection, to be honest, have not implemented this guy yet. Just demand hasn't been particularly high. I think it's useful. I suspect it's useful. I don't know. But this is how it would work. So if you wanted to, you can basically apply namespace to one of these reflection objects. Context, by the way, will give you a reflection of the enclosing context of the declaration. For those of you that might work on Clang, that would be the semantic context, not the lexical context. So you could write using n equals that thing, and then n becomes a namespace that you can use wherever. or a nested name specifier you can use in different contexts. Or you can just use it directly in a nested name specifier and expand to these kinds of things. It seems reasonable. ID expert is actually one of my favorite. I like this one. So if you ask for the ID expression of a named declaration, you get an identifier. Actually, you get an unqualified ID. That unqualified ID typically forms an ID expression that is then looked up, especially if you're in an expression. So if you ask for the ID expert of F, you get the identifier F, which gets looked up. In this case, there's only one definition of F, but because it's just an ID, that could actually invoke an overload set. It's just an unqualified ID. Nice. Useful? Maybe, maybe not, until you actually want to start building IDs. So we actually have a generalization of this that allows you to add multiple arguments in. And I have to be honest, this actually supports the code generation side of this a little bit more than reflection and projection. But you can actually start building IDs. So you can pass in reflections, and that'll just take the name of the reflection and add that to the string. Or you can pass in a string literal, and it'll append to the string literal. You can pass in an integer, and it'll append to the integer. I haven't figured out what else I might want to push in there, but those are the three things that I can do with so far. And we can make IDs like $f function3, and it generates function f function3 for lookup later on. Neat. Because it also generates an unqualified ID, it turns out you can use these to declare things too. So if you really need to generate the name of a declaration programmatically, this is possible. You can certainly do this. And again, this will show up, I suspect, extensively when you start talking about generative and metaprogramming. This is not specifically about reflection, but it fell out of the reflection work. And it's not actually a happy coincidence. This is very much by design. Okay, so implementing stringification in this particular context is fairly easy. That's what it looks like. Any questions? And yes, your optimizer may in some cases reduce that to a switch statement. So what happens is you actually run this through for, oh, I missed a dot. Man, this talk is ruined. Probably ruined when I started. Anyways, so for ... AutoX and enumerators, that will expand to the sequence of compound statements that include the if statement. Each consecutive thing will, oh, that might not, yeah, that might reduce. Basically test for the value and then return the name if you can. I would hope that an optimizer would turn this into a switch statement if at all possible. Not entirely clear. Herb actually gave an example of work that I'll talk about tomorrow where you could do this directly in a switch statement, although again, not guaranteed to work for all enums if you have multiple names of the same value, because switch statements are picky about that. So that's that. The work is very much equivalent to the semantics of 194. I didn't think this when I started, but it wasn't very hard for me to figure out that it was. Going from 589 to 194 is just defining reflexper as the decal type of a reflection. That's how you get there. Now the library and the interfaces, still need to be adapted or whatever, but that's just programming. Going the other way, if you create an object of reflexper type from 194, you get back essentially what is returned by $x. So that's the basic idea. So, of course, because they're equivalent, like we have the exact same problems that those guys did earlier, with one difference. There's one difference. The approach taken earlier, they create a new class for every reflection. We instantiate a template. So, you run into this particular problem. This actually caught me like late, maybe in July. Like I was trying to write a meta program or meta class or something, and I actually ran into this problem and I couldn't figure it out for a little while. When you call a function on one of these reflected objects, you are instantiating the definition of that function. It will not change. You have instantiated it. So, if I have a struct s and I static assert that s is complete, it's not. It's false. That call to s.complete, that locks in the definition, the falsity of that behavior. So even if you define the class later on, it will continue to be false. Which gets a little bit weird if you ask for the members of an incomplete class and you get an empty tuple, and later on you ask for the members of a complete class and you get an empty tuple. Like, oh my god, what's happened? My class has evaporated. Leads to some surprising results. But again, if you depend on the completeness of classes for any part of your design, if your design depends on changing the completeness of classes from incomplete to complete, you probably deserve this kind of behavior. This is not a thing that sane people write programs to do. So, moving forward. Direction was given by SG7 to pursue a reflection approach that included only values, so that we do not create or instantiate types per reflection. In other words, take classes out of the implementation. Values are cheap. They're cheap to create. They don't retain there's no lasting memory footprint for them. They go away, usually. They're simple discriminated unions inside of Clang. Pretty sure they're the same thing in GCC. If anybody here works on Clang, it's called AP value. It's a nice class. So I did this. I have an implementation of that. It's here. It's not complete. I know I have 15 minutes left. I have extra slides I can talk about that, but I'm going to wrap up and give time for questions first. So, I had to. There was a context for all the things. So look, all of the work so far has focused on reflecting properties of declarations, because that's kind of the thing that we want to deal with the most. We want to generate declarations, analyze declarations, write programs that operate over the members of declarations, like specifically classes. There is a whole wide open world when you start moving to reflecting on expressions. Anybody heard of template Haskell? Yeah, that's that approach. So we're not very far away from doing that particular thing, which is a good thing I talked to Gabby yesterday and he pointed me at that so I could look at it this morning. Anyways, so the idea is that we want to be able to reflect. I think that we want to be able to reflect on more things. I don't know yet. I don't know if we want to go in that direction. I suspect that we do. So maybe let's just be reasonable about this and we don't need to const export all the things. We don't need a template meta program everything. But certainly there are times that this could happen. So let's see, acknowledgement, some NSF funding involved here, some support from Microsoft. Thanks to Matt Godbolt for hosting the experimental compiler, although not that one yet, because that's not quite ready for prime time. Thank you for any early users, and stop sending bug reports, please. It's not that I don't want them, it's that I'm moving forward and not trying to be perfective, that's all. So, if there are any questions now, I'll be happy to answer them. Otherwise, I have 10 more slides on the other stuff I've done. Yes?
So back on slide 28, you talked about the kinds of things that can be reflected.
28, you say? Yes?
So I think the fact that you have type ID in the middle of that means that you could reflect on vector int, but not on vector.
So, good question. You can indeed, oh, sorry, repeat the question, I'm being told. I have type ID here yet, which means that yes, sorry, I keep forgetting to repeat the question. Can I reflect on a template specialization, and can I reflect on a template?
Well, I assume you can reflect on a template specialization, but you seem to leave out just templates.
So the answer is that you should be able to reflect on both. I left template name out because I haven't looked at it yet. And reflecting on a template specialization requires a library design that I haven't quite gotten to, but it's interesting. Because you can start for asking for the template arguments of the thing, and you get, like, it starts opening up a brave new world, as it were. Like, get the template from a template specialization, and now our rebind operators go away. Questions? Yes? Ask that one more time.
If I wanted to implement a DSL, could I use the current implementation for that?
Probably not yet. Sorry, the question is, thank you, Jennifer. The question is, can I use the implementation to build a DSL by iterating over members of types and generating new things from these? The answer is probably not yet. More on this tomorrow, but we've kind of had to step back. I've had to step back and rethink how all the code generation stuff works. You can certainly reflect on a lot of things, not templates or template IDs just yet, because we don't have the library design for it. But you can't use that to generate interesting things. Yes?
So I was playing with it earlier,
So the question is, can you reflect on a member variable or a variable and determine whether it is static or non-static, and if so, make it different? Yes. You can detect the storage duration of a variable or member variable, and in the code generation stuff that I am not talking about today, you can actually change as you generate new code whether that should be static or non-static. Sorry, let me clarify. You can make it static, but once you've written something, and this really is about the next talk, once you've written a thing, we don't erase things. If you declare something to be static, you mean it to be static. If you just write int something, you might not necessarily, there may be transformations you can apply to make it a little bit different. But we don't erase specifiers.
So like if it's a member function, like a method,
Yes.
I can make it a static member function and it will be like...
Through code generation, yes.
Cool.
Oh, can I make a member function a static member function through code generation? Yes.
Please use microphones.
Yes, or come up.
We have microphones.
Any other questions? How much time do I have, Jennifer? 10 minutes. You guys want to see what oh, wait, 2 questions.
Just about the slides, the operator can be a type ID.
Yes.
That would have to be what's the expression type ID.
Say that again.
Can that be like a runtime type ID, or does that have to be a constant expression type ID?
Can the type ID be a runtime type ID?
Let me rephrase the question. Can I reflect a type ID at runtime and say, write a function that serializes a std any into JSON?
Can I reflect a type ID at runtime? No. No. That is the syntactic form of type identifier. It is the type that you write there. If you want runtime type information, dynamic cast and RTTI or type ID are your operators.
So type ID, you don't mean std type ID?
No, type ID here refers to a production in the C++ grammar, not a type underscore ID. Yes?
Yeah, on the slides, use the free dot syntax with for loop. I mean, like, lose the dots. It's necessary. You lost one already, so.
So the question is, can we lose the dots on the for loop? And the answer is, evolution suggested no. Because this is not, in fact, a for loop. It does not iterate. It generates code. And so the request was by evolution that because it does something so different, there should probably be something that visually signifies what it actually does. So, dots.
Actually, the question is also about the for dot dot dot. And I think there's already actually a function in 17 called apply, which is basically a one-liner that lets you apply a variadic lambda to every member of a tuple. And it's pretty straightforward to tweak this, so you can also have early exits and so on. So given that, what's sort of the rationale have to do with language feature at all? It seems like for dot 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 is not really necessary. Like, is it compile time or something else?
So the question is for dot 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 really necessary given the fact that we have a function called standard apply? There's overlap. So I think that there's certainly overlap, right? So I know that there are a lot of people in the room who, if they see a for loop, would tell you to use an algorithm, and I don't necessarily disagree with that. But at some point, a lot of those algorithms do reduce to for loops. So if you really want to think of it this way, it's implementation support for the people writing apply. It is implementation support for the people who have to write apply.
But apply is a one-liner, as it is.
Yeah, implementation-wise? I hear to the contrary. You guys can talk about that afterwards. I will bow out. Questions?
FYI, further questions can use the microphone.
Further questions can use the microphone. Thank you, Jennifer. Come on down. I like this. Dance.
Yeah. No, I won't.
Sorry, Roland.
So you have a very simple example here where you pass everything to cout. Could I also use this to aggregate something? No, so, damn it. Can this thing change the type? Like in a fold expression, for instance, if the initial value on the left is whatever. I can pass something in that returns a new type and continue this, for instance, to build a typeset. Can I use something here as well?
So as far as I understand, probably not. You can't change the value of these things as you iterate through them because they expand. You can still carry state, like variable state, through the expansion, but as far as modifying things that you're expanding over, not yet. So there's a limited range of things that you can do with the expansion.
Yeah.
I don't really know how useful it really is in practice. I think the template metaprogramming approach actually gives me more mileage because you can break out early, and we don't have really control for doing that with this. But it was an initial attempt to improve the programmability without opting into sort of much heavier frameworks. Because while 17 might have apply, it does not have boost HANA, essentially.
All right.
Hopefully that answered the question.
Yeah, I'd like to ask whether you consider this like stage of C++ development, the metaprogramming, the final stage of abstraction, because in mathematics we got numbers, then we got groups, and we thought, well, this is pretty abstract, but then we got categories and category of small categories and etc. Do you think it's going to be the same case with C++?
No, I don't really think of metaprogramming as an abstraction mechanism per se. I think it's a tool that you use to buy into abstractions that C++ already has.
Okay.
Does that make sense?
Yeah.
Like,
right.
So I think that concepts are really like the height of the abstraction that we have in C++. Like they specify very broadly what values you have and what expressions or work with those values, right? And almost everything that we do in C++, every line of code that we write in C++ is, at least when you write a class, is an attempt to buy into one of those concepts or another, whether it's default construction or copy construction, or writing the code that locks down a resource container, resource value against moving or against copying, for example, or equality comparison or less comparison, right? So all the things that we build around a class, a lot of the things that we build around a class tend to be very much about the concept that you are trying to satisfy, the thing that you're trying to model. If you want to talk about categories, maybe there's a mapping there. I don't think of it that way, but then I'm, again, not that kind of professor. I write code. So I see this as a way of opting into abstraction facilities that the language already has, not as a way of really making things that much more abstract. And I suspect that if you want to think of it that way, then you might not be thinking of it correctly.
All right, thank you.
Concretely, I had a need or desire for a is pointer free predicate, and is static reflection as proposed necessary and sufficient feature condition for having that?
To detect whether a pointer has been freed?
No, if a class doesn't define any pointers, is pointer free?
I think so. I'll go out on a limb and say yes.
Okay, I thought so.
But don't ask me to put money on that just yet.
All right.
So does this only work for each loops, or can you do for ... open brace and then like a classic C style for loop and like have that kind of work?
For ... and then what?
A C style for loop, like auto I equals 0,
Oh,
I is less than blah.
Can you, so potentially. So what's required, I've actually given this some thought. So what's required to make that loop work for basically expanding over a range is that begin and end have to be constant. Your iterator has to be literal type. Actually, no, you don't even really need an iterator. You just have to do really interesting things. You almost certainly require a random access iterator to do it. But yeah, if you have context for begin and end, and your iterator is literal and random access, I think that you can do that, yeah.
Right. That would be interesting, at least.
It is a thing that I have thought of because of the other 10 slides that I'm not showing.
So you mentioned using the, I think it was like IDExpr or something to define an identifier programmatically. Is that something that you could use to declare an identifier that is not actually normally legally typable as an identifier, such as with a space in it or something, for better error messaging?
Easiest question all day. No. And no, you can't put a poop emoji in there either. I know string literals support that. I don't think I reject that. Better make that fixed before somebody starts abusing it. \u plus.
That's already too late.
Too late, probably. Yeah. Do we have a trigraph for that? Okay, I'm told the session is over. If you guys have more questions, I will be around. Otherwise, thank you for coming.